Okay, so welcome everyone to another talk in the Northwest Database Society series of talks. So today it's my great pleasure to introduce Hangdong Zhao. Hangdong was a student of Paris Koutris at Wisconsin, and he worked on theory of query execution, query optimization, and he's also super interested in making this theory practical. He's currently working at Microsoft, where he is transferring all this theory from abstract concepts into real query optimizations. So without further ado, here is Hangdong. Please take it away.
Thank you, Dan, for the kind introduction. Can the Zoom people hear me? I cannot see any Zoom comments from the. Okay.
And I will let you know if there are any comments.
Thank you. Okay, so thanks everyone for attending the talk. So Dan already introduced me. I'm Hangdong. I'm a current full-time researcher at Microsoft Jim Gray Systems Lab. So just want to have like one sentence explaining what the lab is about. So our lab's mission is to bring research, especially database/systems, now/AI research into real Azure product lines. And then as part of that big effort, I'm kind of working on this aspect of bringing query optimization, especially theoretical part that I'm interested in, into practice. So this talk is actually one of the research line of work that I've been worked on or participated in for the past 2 years. It connects back to my PhD last 2 years of my PhD, and then now at Microsoft, I'm also working on something related to this. So obviously, I need to tell you what is Yannakakis algorithm, and then afterwards I'll tell you like there are two orthogonal directions that I want to cover. The first one is how to make Yannakakis algorithm practical. And interestingly, Yannakakis algorithm has been proposed in 1981 by Yannakakis. But since then, we haven't seen a big wave of adoption in modern databases. So I'm going to cover like why we want to look into that now and what are the progress there. And then after that, there's another, the third chapter is going to be on some theoretical refinement that we've done over the Yannakakis algorithm for the past 2 years. This part can be a bit theoretical, just some spoiler. So I originally prepared this talk under the mindset that Dan and Magda, they have their own groups. I should split it into like half theory, half systems. But now I realize maybe I'm putting too much emphasis on the theoretical part. Anyways, and then I'll conclude with some interesting directions or ideas or things that I've been trying right now. Cool. So it all goes back this talk goes back to the VLDB 1981, where Yannakakis has this paper. It's a bit the font is too small, but basically I'm gonna unpack Yannakakis algorithm in a few slides if you are not familiar with the algorithm. It says the following. By the way, I'm using this notation of conjunctive query. Again, it's kind of database theory-ish, but think of it as like a four-table join table R, S, T, and U, and then they join on some attribute. For example, a table R and S join on X2 as the attribute, right? And then the left-hand side, this is your output, and then output, I'm using a V for view, and then you want the column X1 and X6 out of this. And by the way, in any of the point of the presentation, if something's weird, you can just ask me directly or interrupt me directly. So this query is called, per Yannakakis term, called acyclic. And then acyclic essentially means if you draw a join graph of this query, of this actual join, it's acyclic. In the sense of like, if you put all the tables as your nodes, and your edges represents that they are joining on some attribute, for example, RS join on X2 again. And if this turns out to be a tree, then this is acyclic. So this is a loose term of acyclicity, but for the talk, this suffices, right? So this is acyclic. And then you call that join graph a join tree, essentially, because it's a tree. And Yannakakis says that essentially, if the query, your join, form this acyclic pattern, then you can join in time. So N is I'll use N unanimously in this talk for the input sizes, and out meaning the output size of the query. So that means the size, the number of rows of this table V. So then running Yannakakis algorithm, you can execute this query in input times output time. And then there's a refinement of the Yannakakis algorithm. That is, if the query is in additional free connex is a quite theoretical term, but think of it as like if your output variables are all placed at you can root your tree somewhere, and if that tree happens to contain all the output attributes, then that's free connex, right? So in this case, you want x1 and x6 as an output attribute, and x1 is in R, and then x6 is in U. And there's no way you can root the tree anywhere so that the root contains both x1 and x6. So this is not free connex. Okay. And then obviously if the query only asks for x1 and x2, this is free connex because rooting at R suffices to cover both x1 and x2. And then Yannakakis algorithm has this stronger version says if it's a cyclic and in addition free connex, then you can run it in this runtime of input plus output time. And note that this is not only an upper bound, but also a lower bound because you need input amount of time to read your data into your database and output amount of time to spit out the output one by one, right? So this is, I'm using a big theta notation for optimal. I'll come back to this one in later part of the talk. So what is Yannakakis algorithm doing? The key idea is very simple. It says instead of directly joining these tables or figure out the join order of them, pre-filter them because there could be a lot of tuples that do not participate in the join. So in particular, Yannakakis uses semi-join as an operation to do pre-filtering. So semi-join essentially does something like, for example, if I'm semi-joining S with T, it essentially whatever that remains in S prime are the tuples that must present in T, like must join on T in some ways. So Yannakakis has this multi-passes of semi-joins. Essentially, the first phase is that it creates a bottom-up pass of semi-joins, meaning using, so you lay out your tree in some ways, let's say rooted at R, and then you pass the semi-join from leaf to parents to reduce this S table to become S prime. And then you keep going on and reduce this R prime by using S prime. And then this is the end of the bottom-up pass. Then you go with the top-down. It's a reverse direction. And then you repeat this again until you hit the leaves. So after this, you get a bunch of reduced table of semi-joins. And then you just join, for example, in this bottom-up manner, you join these reduced tables. The key guarantee here that makes Yannakakis very, very interesting, both from a theoretical and a practical perspective, is that Yannakakis have this, people have different names for this. They also call it full reducer. So this is saying that after you have this kind of awkward back and forth pre-filtering, all of the non-joining tables are being pre-filtered by your semi-joins. So that means whatever is remain in this table, in any of the table, let's say S prime prime, this x2, any x2 and x3 in that remaining table must participate in some way into that final output. So there would not be something that inputs are very, very large, but output is like 0 or very few. It cannot happen. So that's the very cool on the theoretical side. This was actually out in 1981. And since then, not a lot of things happen in modern databases. Databases keep evolve as it is, and as maybe people know, that we use cost-based optimization to pick join ordering, and then Yannakakis never show up inside of those. So this, but that doesn't mean that Yannakakis this algorithm doesn't have any value, right? So in particular, this key idea of pre-filtering before you execute joins is somewhat interesting. So we call this pre-filtering. And then this is an experiment that we did on top of one TBCH queries. This is query number 3, where you're joining customer, orders, and line item. So each one of them has some local filters on top of themselves. So a customer, we're looking for a specific type of customers. Same for order and line item, we look for the order date or some conditions on line item date. And then we calculate the number of like rows that after this local filter. So about 53% of the line item rows, we are interested in those for this join. Yeah.
Local filter just means filter on the table.
Yes, local filter means the filter on the table itself. Cool. But these are high numbers, and usually many databases, for example, that I know DuckDB, as of a few months ago, we run this query. It joins customer and orders using this gray part, right? This shaded part and line item. But if you actually count the number of rows that show up in the query results, a surprisingly low number of them actually are useful, right? So these red part represent the number of rows that actually are useful for this query. So that means useful meaning like if you forget about this gray part, you can still execute the join and get the correct result. So for line item, especially the largest table, only less than 0.5% of the tuples are useful for this query. So this is a massive size reduction. And then not only, so the conclusion for this query is that most rows we've seen in this query do not participate in the query results. Cool. So there's also a term for this. So we call this contributing, and this is dangling tuples. But that's just some jargons. So we did this analysis over the whole suite of TPCH to see what's going on there, right? So what's happened. So here, as you see, if I run Yannakakis prefiltering on all of these join queries, so Q1 and Q6, I don't think they have any joins, so I excluded them. But for all the other ones that included join, this is your size of reduction of all the, 13 doesn't have any because of the primary key foreign key joins. There aren't local filters there, but there are some cases where you see massive input reduction because of Yannakakis style prefiltering. So it's order of magnitude reduction on the joint input sizes. However, as we try to understand and we talk to people why this is not, if this is so promising, what is the problem there? Or why is this not adopted? And then the reason, a big reason behind it is that semi-joins are just as expensive as doing a hash join. Because usually for semi-joins, you create hash table, probe it, and it's almost like you're already doing a join, right? So yeah. So as a simple fix to that problem, in Cider 2024, we worked on this, we tried out this cute idea of like, just what if we replace the semi-joins by Bloom filters? So think about it as a stochastic version of Yannakakis, where instead of doing semi-joins, use some probabilistic but smaller data structure. So obviously, creating and probing Bloom filters are cheaper than building the hash table. So the idea we did is very, very simple. I'm giving you another query in case you get bored of Q3. This is a join graph of that query. And it's cyclic, right? Obviously, it has some cycles. It's not an acyclic join. And what we did there is very, very simple. Step one, and this is heuristic, by the way, by no means optimal. We sort the join graph by table sizes. So think about it as some kind of a topological order or some ordering of this by the input sizes. And step two, we create Bloom filters from the smaller one and pass it to the bigger one and go on and on and on to the biggest one, which is line item. And then afterwards, we do a reverse pass of reverting every edge backward to filter back. Right? So this is obviously not optimal. There's many ways you can engineer this to make better results. But that's what we did as a first trial of experiments. So the other good thing is that if we do it in the general way, we don't have to think about whether it's acyclic or not, right? We just for any acyclic or cyclic joins, you can pass it, and this already gives us some big gains inside of some of the databases. Yeah.
So what are the Bloom filters over, and what does it mean to transfer Bloom?
Yeah. So I should make that point clear. So for example, here I'm creating Bloom filter on the region table. And then I pass the Bloom filter to, because region joins with nation. So I pass that Bloom filter to filter nation. Okay, so now nation gets filtered by the Bloom filter from region. Then I'm gonna create two Bloom filters from nation. One passes to supplier and one passes to customer. And then supplier got reduced because of nation's Bloom filter, and then keep repeating this process until you hit line item. So this is one pass, forward pass, and then you revert it being the backward pass. So think about it as this is also called sideways information passing in many literature, in a sense of like if you pass your Bloom filter in this way at line item table, it's not only that you're passing the information from orders to line item, you're also passing all of these tables information into line item through the Bloom filter. Cool.
This still requires enumerating like all the tables. Is that compared to the Yannakakis algorithm, we are saving the semi-join with Bloom filters?
Yes. That's a good comment. So instead of using semi-joins, every step we use Bloom filters. And then Yannakakis would ask for a join tree, or would just do some simple heuristics, small to large. So yeah, this has been quite good. I'm not showing you the numbers, but it's pretty good results that we get on many modern databases. That we just tried by rewriting the queries and stuff. So after this, there was a line of pre-filtering ideas of research along this Yannakaki styled pre-filtering ideas, and I'm only showing you some of the papers I got that I found on VLDB 14. Sorry, 24, 25 VLDB and Sigma papers that are already accepted. So there are others that I haven't included. Some are in archive, some are here and there. I haven't included them. All right, so a bunch of them. In particular, I'm going to highlight one that I did, which is a bit of a bragging, but it's going to appear in next CIDR 26. So I have a fun story of this. After we had this initial predicate transfer paper, I luckily I was a theory person, so I was hopeless and had no jobs, no intern offers as well. So at that time, Great System Lab reached out to me and asked whether I'm interested in considering an internship at their lab, and then thinking of trying to see if there's a way to implement predicate transfer or Yannakakis into Microsoft SQL Server. Okay, so their motivation behind this is that they know that SQL Server already have Bloom filter, aka in their terms bitmap filters, but similar terms. So I started an internship. I was very happy in Seattle, that was summer of 2024, and turned out the summer was a struggle. The reason is I spent 3 months crunching SQL Server's code and understand the query plans, understand how it does. I know that it has Bloom filters, how it works exactly. We don't know, and I'm digging that out. And at the end of the internship, it was a bit of a bummer. I was asked to see if there's a way to improve SQL Server using predicate transfer, but instead, this is my message that I got from this internship, that SQL Server has implicitly subsumed Yannakakis or predicate transfer in its cost-based design, and that confirmed with the engineer has already been shipped in production since a decade ago. So that was kind of sad. I didn't make any, unlike other interns who made a lot of successful code changes, I made 0 lines of code changes, but I found this out. So I said, like, why don't we write a paper about this? So now I joined full-time, and the first thing I want to do is to write this paper. And this paper is going to be out very, very soon. I'm still preparing for its camera ready, so I haven't actually figured out the best way to present it that do justice both to Microsoft SQL Server and to the academia people. So watch out for that.
So after this failed internship, they made you a full-time offer immediately before.
A few months later. Yeah, but I don't know whether this is a successful story or not. So I haven't figured out a way to tell you how Microsoft SQL Server does it, but I do want to show you a peek of the result that we have in this for Microsoft SQL Server. So this column is the TPCH queries again, 1 up to 22. And then there's a lot of redundant information I don't expect you to read. These ones about speedups if you enable Bloom filter features inside SQL Server. So almost all the queries got some speedups if you use Bloom filters, some by a big amount, like say this one, 3x. So what is interesting again is you look at the last 3 columns of this table. So I'm using query 3 as another example. The example again. So this 400 million rows is the rows that you're going to read if you only apply the filters on the table itself, right? So customer orders and line item, they all have their respective filters. You consume them, you still need to read this amount of, assuming these are filtered, the others are filtered away. But if you use SQL Server, if you look at how much SQL Server actually reads, there's only 5% of that for 400 million rows that are read by SQL Server because of SQL Server's internal mechanism to do Bloom filter parsing. And then then this was something I did manually. I tried to force Yannakakis being run, like forces to run Yannakakis style pre-filtering and get the absolute lowest number I can. So this is 1% if you of the tuple that participate in the join after doing Yannakakis semi-joins. So, and then you see across the board, right? So many queries, the SQL Server's pre-filtering already get a decent, most of the benefit out of it, right? So there are some that still show some gaps, and the gaps are like the red ones are the ones that show some percentage gaps be above 1%. And this is because SQL Server using cost-based decisions doesn't always impose Bloom filter that aggressively as Yannakakis. Sometimes if the selectivity is below a certain threshold, it won't do it because it just incurs extra overhead. And also because it carefully decides the Bloom filter sizes and all, there's also a false positive rate that could amplify, especially when you have multi-passes. Anyway, that's a short summary of the paper. And then I definitely, if you're interested in this line of work, definitely look out for our paper once it's out. So I'm gonna check on time. I have half an hour.
Oh, yeah.
Okay, I'm going quite fast, actually. If I was expecting a lot of questions, but not. Yeah, so any questions at this point? Yeah.
So in the Yannakakis column, is this with using Bloom filters or using semi-join?
They are using semi-joins. They are handwritten SQL by me. And everything is using perfect semi-joins, assuming perfect filter. Yeah.
So some of the losses between SQL Server and Yannakakis may come from the false positive rate of.
Yes. Some missing gaps are because of that.
Thanks.
Yeah.
What's the optimizer slowdown?
Oh yeah, that's an interesting part. So this part is largely being ignored by many papers that I've known out there, which is like if you added Bloom filter into the optimizer decision kind of space, right? So there could be untrivial blowups of things and plans that the optimizer need to consider, right? Like because in addition to join order, you also need to determine what Bloom filter is doing, where is passing to where, from where to where. And then also Bloom filter can have a non-trivial impact on the cardinalities. And then you need to factor those into your query plan, like join ordering as well. So for a long time, even for SQL Server, people need to understand how to control the optimizer overhead as well. Not to consider an explosive space of query plans, but to focus on those that are actually promising. Yeah. So the ones that has a triangle on top of them means there are some observable optimizer slowdown because I enabled Bloom filter features. And by the way, Bloom filter features already in SQL Server. If you download today using SQL Server, it's there. This experiments I manually had to turn off Bloom filter to see what's the speed up or slowdowns actually, and then yeah.
No, it's on by default. It's shipped.
It's on by default. It's already shipped. Yes. Cool. Yeah, so next is a bit of a theoretical part. I will try my best to explain it. If this is too complicated, sorry. As always, I want to start with some good stories on this. This is some paper, some effort we did back in 2024. Along with another effort I was doing on predicate transfer, we were also thinking about can we improve Yannakakis from a theoretical perspective. And luckily, we got best papers out of this. And in parallel of our efforts, so we have this paper out there. There was another paper from Zhao, a professor from University of Waterloo, and then she tackled a very similar problem and using similar techniques, and arguably she gets a better runtime result than us. And after we both got POS best papers, we were asked by POS PC to merge them into one paper and submit it into JACM, Journal of the ACM. And then that's the part we are debating now, because we both have a different version of the algorithm. One is simpler than the other, but the other gets better result than the other, right? So we need to figure out a way to uniform both, merge both paper into one framework. So I'm not going to tell you any of these two papers. Rather, I'm going to tell you our plan about how to merge them into one. And this is a proposal.
So can you try to move that window?
Oh, yeah.
Make it.
Or maybe we can just minimize that.
This better? Yeah. I didn't expect something to be here, so I try to use the whole space of my slides. But anyway, so recall that I'm using this. I will use this as an example of a query. That's a path. We call it path query, but that's because the join graph of this query is essentially a path. We're joining R, S, and T, and then the output you want is X1 and X4. That's why I use solid circles for the endpoints. We want those in the output. And then recall that per Yannakakis' terminology, this is not free connects because there's no way you can orient the tree so that 1 and 4 show up in one table. So it's not free connects. And then if you remember from, oops, I cannot move anything now.
You just click on it.
Okay. If you recall, this is not free connect, so you can run it Yannakakis using input times output time. That's the runtime. But if you use our proposal, which is called output sensitive Yannakakis algorithm, and we are submitting it right now, you can join it in time input times output to some 1 minus something plus output size. So this minus factor 1 minus 1 over W, this is the gain that we get comparing to this. And then for example, right, in this very query, we can show that this W is equal to 2. So that means you can actually run the query in time n times square root of out, shaving off a square root of out factor from Yannakakis algorithm. And this W, if you want to know, is called free connects fractional hypertree width. Just again, some jargons there. And then what's interesting about it is that this bound is tight, whereas this bound was not. Remember that there was a free connects version that was already tight, but this one, the tightness was open for a bit. So that was quite exciting. So yeah. So I'm just gonna tell you like what's the high level things that we do to make for this output sensitive Yannakakis algorithm. So Yannakakis algorithm, even though it takes down a join tree, so this will be a join tree for the Yannakakis algorithm, it follows one join ordering on that join tree, right? So for example, if you root it here, that it is implicit that you join T with S, project out X3, and you join the result with R. Okay, so Yannakakis, you would need to stick to one tree and then join on top of it. And output sensitive Yannakakis is different in the sense that it needs to identify for certain parts of your query, like certain parts of the data, because of the special characteristic of that part of the data, you might want to use a different join ordering for that subpart. So what does that mean is like, obviously here for this query, you have two join orders. Forget about the other weird notations here. There you have two join orders. One is you can join from R all the way to T, join with S and join with T. The other one is you can join T with S and R, right? It's hard to tell which one is better if I just give you those information. So turn out that there's a way, theoretical terms that you can capture those join project ordering. So here I'm showing you two trees. These are no longer join trees. These are called free connects decomposition. But think about it as the following, right? So if I give you this kind of a tree, think of it as I want you to first compute a view, given your base table, compute a view containing x1, x2, and x3. And in this context, it means join with R and S. right? Potentially project out x2 because you don't need that anymore. And then after this query, this tree says, next you need to compute v2. Is a second view that is take your result of v1, which is 1, 2, 3, and join with t to get the result. So this is what this tree encodes. So similarly, this tree encodes the opposite direction, join t with s, project out 3, and join with r. Okay, so these are the two plans that that is there for this query. So why do you want to use multiple plans instead of Yannakaki style of just pick one plan, run it? The reason is Yannakaki style semi-join passes can lead to implicit but strong degree constraint, which this part, just understand it as using semi-joins, the data can behave in certain ways that you can leverage to give you a better runtime. And then this part is also inspired by the Panda algorithm that using different statistics of different parts of a plan can benefit from a different query plan. So meaning that if I give you a query for certain part of the query, certain part of the joins, running plan number 1 is better. Whereas for the other parts, running plan 2 is better. And then we want to make the split so that each part goes to their respective query plans. So how does that, so I'm gonna skip this part. How does that work? This comes from an idea of, we call it progress tracking. Think about it as this. If you have this query, remember this was the one that we want to address. And then these are the two plans that I've drawn. So one joins from R to T, the other from T to R. And think about it as this. When I ask for this join, you don't know whether you want to join RS first or ST first. So let's do the following exercise. Let's try to partition the data so that the query becomes 2 fragments. And then for one fragment, you computed V1. And for the other fragment, you computed V3. So you're kind of making progress on both subproblems. It's just that one subproblem makes progress here, the other one makes progress here. Okay, so that's the first step. I haven't tell you how to partition it, but imagine there's some magical way to partition the data so that you know some part goes to V1, some parts goes to V3. Okay, I don't know if I'm losing the audience, but cool. So let's look at the branch that actually computed V1. So I'm shading V1 to denote that we've already computed V1 for that subproblem, right? Remember, we have 2 cases. I'm looking at the first case where we computed V1. So in those cases, I want you to make another decision because now you don't know whether you want to compute it V2 or V3, which one to compute. You don't know, right? So I'm gonna do another partitioning and say, what if I partition my data again to half so that for one subproblem you computed V2 and the other subproblem you computed V3. Okay, cool. So for that subproblem that computed V2, remember you've already computed V1. So this means you've actually formed an entire join tree, a free connex decomposition, but you form an entire plan. You materialize the 2 views, and now you are ready to run your join. And then you're done for this subproblem. But for the other, it might be that for the other subproblem that materializes V3 instead of V2. In that case, you need to make another call of which one you want to compute next. Which progress you're going to make next. So this is called progress tracking in the sense of you know your progress of for that subproblem, you already computed V1 and V3. You want to pick of V2 and V4, which one to compute next. So for now, it becomes simple in the sense of if you partition the data and one part computed V2, then this tree is ready. You can compute it. And then for the other part, V4 is ready. You can compute it. And then the algorithm is partially done. You're done for the V1 branch, but also for the case of V3, you need to also do this trick of playing with what's next, right? And you partition and make progress simultaneously on both plans. Yes.
Are you going to show us how you partition?
Yes, I'm going to show how to partition.
Because my guess is it's going to become clearer then when we understand how to.
Yes. Yeah, agree. But that's the high level idea. For now, I'm just imagine that there's a magical way to partition it so that you can compute in this way. And this is the way where you kind of get the final query whenever. So like, actually, I'm just gonna ask a question of like, how many sub problems or subqueries are there if I partition in this way? In total, like I have this original query, and if I go with this partitioning schema, how many subqueries do I have?
Or no. You have
So obviously this is one.
Yeah.
There are two, so that's three. And you have another case that's the symmetric, so you have another three. So there are 6 subproblems. Okay, and for every subproblem, you would generate some output, and you union those output that get back, that you can provably show that recovers your query results. You covers this table. Cool. So now I'm going to show you how to make one progress, because I've been saying that we can make progress. How to do that? So imagine you are starting from scratch, and you have that query, and I'm saying you don't know which one to compute, so why not partition your data into 2 so that one part to go to V1, one part to go to V3. But how to do that? And in particular, I'm going to show you that we can make progress in time and square root of out. And this is where the runtime complexity comes in. And then the idea of doing so, it's very simple. You take your relation R and you partition by the degree of x1 given x2 by its heavy or lightness. So for the heavy part, we'll have a different treatment than the light part. By the threshold of so we partition it by the threshold of square root of out. For now, just assume that we know the output size magically. There are ways you can remedy this, but assuming you know this. So then you partition it in 2 pieces, light and heavy. Okay. For the light part, you can join R1 with S. And this will help you materialize this. And because you know for every binding of x2, there are at most square root of out number of x1s. So this join is bounded by n times square root of out. So that's the easier part. The other part is that what if this is heavy? And if this is heavy, so I skip this observation here, but I'm just going to tell you what's the conclusion of that, is that if R is heavy, then you are looking at this query, right? R2 means the heavy x2 values, R2 for the heavy x2 values. And then after running Yannakakis style semi-join, you can show that the number of distinct x2s are bounded by square root of out. This is because of the following. Let me backtrack a bit. So my slides organization was pretty bad. Yeah. So here it is. Suppose you have table R S at T, and then after semi-join passes, and then now I'm showing you all the x2s being heavy. Heavy meaning in this context, heavy by 3. So every node has more than 3 connections in x1. And since it's after semi-joins, so you know that every x2 should join with some x4, right? Because
And
yeah.
a dark node in x2 doesn't mean anything, correct?
Dark node doesn't mean anything. Yeah, doesn't mean anything. Yeah. So now you can show that if this is true, that every x2 values connects to more than 3 neighbors of x1, the number of x4 is bounded by output divided by 3. And why is that true? Because if you have more than output divided by 3 number of x4s, for every x4, there are connected to some x2 values. And for that x2 values, you have more than 3 number of output. So that means your output size is bigger than out, which is a contradiction. Okay? So that's the guarantee that we're using here. So let me come back up. Yeah. So in this query, if this is heavy, then it means the number of x4s are bounded by square root of out. And in that case, you can join S and T, and you're bounded by n to the square root of out, because the number of distinct x4 values are bounded by square root of out. And then if that's and then you already you finished your progress, this progress, because the light part, you partition into 2 pieces. One piece is computed V1, and then the other piece is computed V3. and you rinse repeat to make progress on both tree until you solved all your 6 subproblems, and then you union 6 pieces of results into one, and that's your result. Yeah.
Sorry, don't these two cases already cover the entire space? Because you only every X2 is either light or heavy, but you seem to have covered both the light ones and the heavy ones.
Yes, but that means I've made progress on these two. I have made a progress on computing this or this. So you have for each subproblem, let's say you computed this, you need to make another call of computing V1 or V4. So that gives you the second progress you're going to make. So by progress, I mean computing one or the other.
So why is V1 and V4 not independent?
V1 and V4 not independent? What does what do you
I
mean?
thought because you have already partitioned your data, so I saw like V1 and V2 is like already computing half of the query result, and V3 and V4 compute the other half. So why not just? So I thought like the query plan, the join graph on the left is independent of the join graph on the right.
Yeah, they are independent.
So you just.
But you are making progress independently on both. In a sense of think about it as this, or think about philosophically like this. You have your start. You start by having some data, and then you don't know which one you're gonna compute that's cheap, right? You just don't know, and then you try both simultaneously, and then you make progress on those simultaneously until one tree gets completely executed or one plan gets completely executed. And at that point, you declare victory for that subproblem. So that's the high level idea. So you have your data partition, and for every partition, figure out which one is good, and you make progress. So from a global standpoint, you are making progress simultaneously on both plans. Yeah.
In that case, where do the 6 combinations you mentioned come from?
Yeah, so let me backtrack a bit. So initially, you have your data and you need to make a choice of which one to go. Instead of splitting into 2, and then this generates 2 sub pieces. One computed this and one computed that. So symmetrically, so let's just look at one instance where I only computed V1. So there are 2 subcases computing. The one computing V1, you need to split that further into 2 subproblems of computing this or this, V2 or V3.
Okay.
And then if you computed V2, you're good to go. So that's done with one subproblem.
Yeah.
The other subproblem is if you the other 2 subproblem comes from when you computed V3, you need to make a call of computing V2 or V4.
Okay.
If you computed V4, this tree is solved. The other one, this one will be solved. Yeah, subproblem 3. And then mirroring back, you have the case where you first starting with V3 instead of V1. So you have another 3 cases, 6 cases in total.
Thank you.
No problem.
So why does the order of computing then matter?
Why does order of computing, you mean why do I want to go bottom up?
No, like why? So for example, the order V1, V2, V3, V4 versus the order V1, V3, V2, V4. Like, why do I need to consider both?
In the sense of why do I need to consider V1 and V3?
I guess so. Like
Yeah.
In total 4 steps, right? Like
Yes.
you want to do V1 before V2 and V3 before V4.
Yes.
That's the only constraint.
Yes.
So why does the order of why does the order matter, right? It seems like
you mean
you're
like
computing the result eventually.
yeah, you mean like why do I need to why can't I start with V2 or V4?
No, like I know like you need to start V1 and then V2.
Yeah.
I'm just asking like why do you need to consider all different interleaving of V1, V2 and V3, V4? Can you just choose one and commit to that?
Yeah, the thing is, there could be a subproblem that goes into the direction that you haven't covered yet. So if, for example, I only go with this, and I call it a day, it could be that there are some data that initially partitioned into V3, right? So for that subproblem, you need to make a call of which one to compute, because that's in neither of those categories that you previously computed. So you need to cover all possible cases. In terms, think about like you need to cover all cases where you can make progress, and the data can make progress in arbitrary way, and you want to cover all of the possibilities. And then the upper bound will be bounded by the worst progress, like the most expensive progress you're gonna make along this this line. Yeah, it just happened that in this case that all progress can be bounded by n squared root. Okay. So last part is some of the open questions here. There are many of them actually. I started a list, but I only want to highlight 5 that I'm most interested to me. The first one is Bloom filter aware query optimization. This one is being studied to some extent, but not much, I'd say. So I wanted to bring it again to the audience. For example, an interesting question is how to do cardinality estimates on the Bloom filter impacts. So Bloom filter can give a big impact on the tables cardinalities, and especially sometimes we might misestimate the selectivities. And then that if the Bloom filter turns out to be not useful, we're just plainly adding overheads. So what we want to be what's the way of accurately estimated? So I was actually talking to Dan a bit before on is there a way to use LP bound to capture this? And obviously that also leads to a question of when or when not to use Bloom filters, in which directions to pass Bloom filters. These are right now in most literatures I've found, also in those VLDB Sigma paper that I've presented earlier before. They are all using heuristics, like including the predicate transfer paper and the follow-ups. They're all using heuristics in the sense of like small to large, or following some joint trees or spanning trees or whatnot. But in practice, you want everything to be in cost-based decisions, right? So sometimes maybe small to large is not the best heuristics, right? Or if you have both sides are equally large, then which direction you want to go?
And from a more systems perspective, the kind of performance characteristic of the Bloom filter is it works fine until it saturates and then really drops off. Is that
a performance of Bloom filter itself?
Yeah.
Yeah, usually you would want for a Bloom filter that are heavily contained, I mean a lot of ones in it. It's not going to be very useful. It's not performant as well. It's just a lot of overhead. Yeah.
But is that part of the?
Yeah, that is part of the picture. Yeah, yeah. And then also depends on, for example, how many distinct key values that you have. You might want to create a Bloom filter of a different size to fit that. And sometimes depending on the statistics, like you may have a very compact value domains. In that case, maybe Bloom filter is not the best. You might want to use a bitmap, a bitmask or something. And sometimes people also use zone maps for the ranges instead of just Bloom filters. So these are all things that are not being well studied yet. So that's one. And second is that so there are some papers also about the showcasing one particular good aspect of the Yannakakis style algorithm, which is called robustness. So in that context, it means like after you run this semi-join, you pre-filter your data, so it reduces your input size. Basically, everything joins, and then the remaining, like the join order doesn't matter that much after you have pre-filtered the input table. But obviously, this thing doesn't hold for cyclic joins from a theoretical perspective. And then in practice, people do care a lot about robust query execution, but we care it at the extent that we don't want to incur a very obvious overhead. If using robust execution means 80% of the query becomes 5% slower, 10% slower, maybe that's not a good thing to have, even if we save that remaining 20% by a big factor. So yeah, robustness is also a good direction to look at, and robustness especially with less overhead. And third is that the area that I've been actively involved working on is like, can we try this pre-filtering techniques in the cloud databases? So that the context becomes not only to pre-filter the data, but also reducing data shuffles. Because for distributed or large scale distributed hash joins, you need to move a lot of data around. And if not many of those are not actually useful, you might want to pre-filter them before you join them. But there's a lot of different considerations and problems or that you want to consider in that context instead of a single node databases. So that's also an interesting perspective. And the fourth is I also talked about this output-sensitive join algorithm for the theoretical part. I've also been looking into whether the idea of partitioning the data and for each piece of the data run a different plan, a different suitable plan for that part of the data being practical or not. So we had some results on this for cyclic queries running on DuckDB and Umbra. Basically, if the query itself is cyclic, we manually partition it and then run that query asking the optimizer to run different plans for different subpart of the query. And for those very cyclic queries, it becomes very effective. But it's unclear if it has any impact in normal like cyclic queries or normal acyclic queries or queries that doesn't have a big skew. So that's also an interesting aspect to look into. Lastly, is for me, so I'm a researcher. That means I can spend roughly 20–30% of the time on theoretical problems that are interesting but take a while to translate into product. So I'm interested in how to translate these kind of algorithms or the output-sensitive Yannakakis algorithm, something like that, into a tropic framework that Dan and other people have been developing over the past years. So yeah, that's all for the talk. Thank you very much.
So at this point, we need to stop the recording. And